Welcome to the 6th episode in a series for calculating pi on my relay computer. Here's a journey so far. And it started with the challenge to calculate pi to 20 decimals, but on my relay computer, my basic, limited, electromechanical 8-bit relay computer. And although the journey may be long, we're well on the way, so there's no turning back, and therefore on with the goal. Precision of pi that my computer needs to calculate. How so? Well, there's many ways to calculate pi, but I've settled on a binary-friendly infinite series, the Borwein Plouffe formula, or BBP for short. Tiny issue though, BBP produces pi in base 16 not decimal, but that's okay as we can convert between the two. And so I converted the BBP formula into high-level pseudo code, and built up a shopping list of the functions needed. That is, the things my relay computer can't do natively. In episode 4 I set out an approach for dealing with long addition, so we're ready to start coding that up. However, last episode we hit a bit of a roadblock around my computer not being Turing complete, and that meant none of this was possible unless I did something about that. And do something about it I did, and by the end of the episode I was able to demonstrate loading and saving values into memory, which was the missing secret sauce to Turing completeness. So, there's no excuses now, and we're back on for calculating pi on my relay computer. In this episode then, I want to get some progress made on the long operations, and given we've got a high-level approach for the long addition, let's get that coded up first. So here we are again in my Relay Computer IDE, which is available at editor.relaycomputer.co.uk if you'd like to play along. I'll be writing the long addition routine in my custom Relay Computer assembly language, which is kind of a mashup of various 6502 and Z80 assembly languages. The key point is the vast majority of what I type here has a one-to-one relationship with the opcodes my computer runs on, and, for example, if I type an add instruction here, you can see that it generates an 81 in the output window at the right, which is the opcode for an ALU add. Using assembly language this way keeps me close to the architecture of my computer, but also keeps things readable enough to make programming less of a chore. To get us started then, I've got a comment block typed up which explains what it is I need to write, and that's always a good place to start. I've also added a known sum that I can test the code with, and this is the example I worked through back in episode 4. At the bottom is a long addition we're looking to carry out. The second row is added to the first row, producing a result in the third row. To save space in memory and simplify the code, we're going to overwrite one of the values with the result byte by byte, which effectively makes the first row an accumulator. In the middle here you can see an example of where we've already calculated the first byte overwriting memory location 7. It's set to C7 because adding 35 hex to 92 hex is C7. We're using the Y register to reference the current byte of the org end. That is, the number to which another is added. Similarly, we're using register X to track the current byte of the add end, the number which is added to another. Now, bear in mind we have a 16-bit address bus, so we're only tracking the low byte of that address, which means that our add end and org end need to be in the same page of memory. We could of course store the full 16-bit address of each, but we need to be frugal with the registers we have available, so make trade-offs and compromises in our program design. One challenge we had in episode 4 was that we needed to decrement X and Y to point to the next bytes in memory, and given my computer is much more suited to incrementing over decrementing, we just store the values in reverse byte order with the least significant byte first, and that means our X and Y registers start at 10 and 0 respectively, and can then be incremented by 1 each time to move with the bytes. So first thing we need is the values we'll be adding together set in the computer's memory. Well, how do we do that? Well, we can certainly store executable opcodes in memory, but again it's all just ones and zeros to the computer, so those values could be data instead, and we just need a way of inserting them into the assembled output. And we can do just that with the byte directive. Here we're asking the assembler to write literal byte values straight into memory, and then to keep track of where each value starts, we apply a label. Note that the values are in reverse byte order, that is, they're little endian and start with the least significant byte first. Looking at the assembled code, you can see the values written out verbatim. Note that if we set the program counter to point to SA and hit the run switch, the computer would actually try executing these as instructions, so we have to be careful to make sure that doesn't happen. One thing worth mentioning here is the align directive, which ensures the memory location of the next instruction or byte of data is rounded up to the next 16 bytes block of memory. That just makes it easier to see in the emulator, and it's totally optional. Right, let's get the X and Y registers set up, and the quickest way to do that is via the M register, making use of the 16-bit load immediate instruction. Now there's a bit of Paul Law magic going on here, where I've introduced a special symbol to pack 2 bytes into a single 16-bit word. The symbol choice is a bit arbitrary, and just happened to be something on my keyboard that didn't clash with other common programming symbols. If it turns out to be a bad choice, of course, I can just change it in my assembler and so on, but for now it'll do the trick. And looking here in the output window, you can see the low byte of label SB and the low byte of label SA. These will change, of course, as we add more lines to the program, but the great thing with labels is the assembler will keep track of everything for us. The 16-bit load immediate is actually a form of goto instruction, just that we load M rather than J and never take the jump. That also means it's a 24-cycle instruction, but that still works out cheaper than loading the registers individually, and here we're not limited at all with the value we can load, whereas the 8-bit load immediate can only load values between -16 and 15. Next, we can take advantage of the 16-bit move to get the value in M over to XY. And with that, X now points to the first byte of the addend, and Y points to the first byte of the orgend. The next setup task we need to do is setting the D register to where the addend ends in memory. In our diagram, that will be address 18, like so. And to arrive at that in code, we have the following. So we load B with 8, the number of bytes in our sum, and then we can pull over the addend start address from register X and add them together into register D. The reason we take the length of the addend rather than the orgend is because we might want to add a shorter number to a longer one, and there's no point adding 0 bytes unnecessarily, so we can stop earlier for a short addend. In all cases though, the space reserved for the orgend must be at least that of the addend, and we must ensure we initialised all bytes of memory in both to ensure we don't pick up random values in memory. Finally, we clear the M1 register because, in this example at least, we know the values will be in the same 0 page of memory. With that, we're set up for performing the long addition, and given comments don't impact the assembled program, let's treat ourselves to a few extra here. Which reminds us what's in each register by this point in the program. We can now get the byte add underway, and in our diagram let's take the case where we're pointing at the next byte in memory, like so. We can now copy register X to M2, thereby pointing at the next addend byte. And we can then load register C with that byte. We then copy register Y to M2, and we can load register B with that byte. We now have our 2 bytes in registers B and C, so we can perform the ALU add to register A. Finally, we store the result back into memory, and handily we're already pointing at the right location via register M. And that's the byte addition complete. Next, we want to increment our X and Y pointers with a code as follows. Here we start with the increment XY operation, but effectively that only increments the Y register, so to increment the X register, we copy X to B, perform an LU increment to A, and then copy A back to X. X and Y are now referencing the 3rd byte of the addend and orgend, and that sets us up nicely for the next block of code, where we copy D to C and A to B. And we can then compare them to see if we've completed the overall long addition. Note here that CMP is actually a synonym for EOR, and in either case they assemble to 85, which is the opcode for an ALU exclusive OR. In fact, in the output window here, you can see that the 85 is considered an EOR, even though we typed in compare. That's because the disassembler is looking at the opcode in isolation of any context, and it just assumes it's an EOR. Again, it's all the same to the relay computer, it'll perform an ALU exclusive OR regardless. So what's the result of the compare? Well, exclusive OR sets a result bit when one of the input bits is set, but not both. Our result therefore is 0A. If the values are exactly the same, then we get a hex result of 00, and the ALU would set the 0 flag. Here, our values aren't the same, and so the 0 flag will be cleared. As such, we use BNE branch if not equal to jump to the loop label if the 0 flag is clear. That is, if the result of our compare indicated the values were not equal. If they were equal, however, then we're done, and we'll load the M register with a start address of the orgend SA and halt the computer. The load M is totally optional here, and it's just a convenience measure for the user. There's one last thing we need to implement for our long add, and that's carry handling. Let's update our example diagram to where the next carry would happen. And on this calculation step, looking at the B and C registers, we have 4 plus 4, which is 8, and then 4 plus C, which gives us 0, carry 1. So in this case, our ALU carry flag is now set, and we need to enter a carry handling phase. To do that, we add a condition jump here. And that's just saying branch to the carry label if the last ALU operation set the carry flag. BCS, branch if carry set. We've got an assembly error here, of course, and that's because we've not defined the carry label yet, so the assembler can't write out the address to jump to. To apply the carry, we need to go to the next byte in the org end and increase it. Here's the code for that. And we start by incrementing the M2 register, and then loading the byte into register B, performing an ALU increment to register A, and finally storing the value in register A back into memory. At that point, there's a couple of decisions to make. If that increment caused another carry, then we need to repeat the carry operation again. We do this with another branch carry set. This would only happen if the current byte was FF, so typically this jump won't be taken. And if that's the case, then we're good to unconditionally jump to the continue label and add the next bytes pointed to by X and Y. And that's it. That should give us the result we need. Let's give it a try. So we can see the emulator has already loaded up our assembled code and is ready to go. Our starting org end is aligned to the fourth row of memory, which the assembler has achieved by padding out with zeros here. 8 bytes further on is where our add end starts, and as expected both values are little endian, stored in reverse byte order. So let's run the program, and the org end is overwritten with our expected result. In terms of runtime, the emulator estimates it would take 2 minutes and 19 seconds at a default clock speed of 6 Hz. Well, I guess that means it's time to try this out on the real relay computer, although our programs are starting to get longer and longer, and to be fair, I'm not particularly looking forward to keying this one in. To give you an idea what I'm banging on about, there's some export options in my IDE, and one is what I call a load sheet. Oh, and mind your eyes if you're watching in a dark room, as this is going to be a bright white background. Ready? Okay, here comes the click. And for each line I need to set the main panel switches accordingly and then hit the deposit button. Yeah, quite a lot of finger work, eh? Now, I knew this was going to be a problem at some point, so I also created this. And the idea here is that you can print this out, cut it up into strips, and then feed the strips into the computer one at a time. My thinking here is that in the computer there'll be an optical reader that sets the data bus accordingly and then flicks the deposit next switch for each line. Now, none of that exists yet, so it'll be a video for another time. But in the meanwhile, I've nicked an idea from fellow relay aficionado Dipdot. And he's been using an Arduino and relay board to test his creations, which is wonderfully flexible, quick and relatively simple, and I'm ever so slightly embarrassed not to have thought of it myself. Anyhow, let's use that to load the program up and give it a whirl. So here's my Arduino clone, and I've gone for the 2560 as it's got plenty of digital ports to play with, which is just as well as to the right here is my 16-channel relay board. From there it's all a bit Island of Dr. Moreau, where I've conjoined the relay board with the buses and control lines of my relay computer. I've also tapped into the computer's 12-volt rail to power the relay board. Now this is all janky as hell, but hopefully a temporary measure for now, and I'll do something prettier with a tape reader at some point. On the other end of the Arduino, following up the USB cable, we've got my MacBook ready and waiting with the long addition program. To get it into the Arduino, I first need to export the compile program to the clipboard, and this is literally just a hex dump of the assembled program prefixed with where the program should start in memory. At the moment that feature's not used anywhere, so it's always just address 0. Over in the Arduino IDE, I've got my rough and ready loading program, and all I'm doing is waiting for a string of bytes to come over the serial port, and then once received I'll chop it into groups of 2 hex characters, pass out an 8-bit value, and then I can set the data bus like so. And then finally I perform the deposit next cycle. Now this code could probably do with a bit of a refactor and a tidy, but it'll do for now. So we're already connected to the Arduino, so all I need to do is paste my hex code and then hit enter. And there we go, program loaded. And that's a lot easier than entering it by hand for sure. Right, let's give it a run. And with the ding, we're done, and the M register is now pointing at the start of the result in memory. So let's read out the expected value, which will be in little endian order, of course. And we've got C7, C, 82, 69, 08, B1, 23, and F1. Perfect, just as expected. So I think we can confidently tick off long addition now. Right, how are we doing for time? About 20 minutes in? Okay, let's squeeze in one more for this episode, and I think long subtraction is probably next, given it's very similar to long addition. Let's get back over to the IDE. And we'll kick off with a completed code this time, but I'll quickly run through the differences. At the top here you can see the trick we're going to pull. We want to subtract SB from SA to get the result at the bottom. Well, if we negate SB first, then we can just add the two values together with the long addition approach we've already proven out. To negate a number in binary, we perform a 2's complement by inverting all the bits and adding 1, thereby making it a negative number. Scrolling to the bottom, you can see our two values, and, as before, they're stored little endian in memory to make stepping through the bytes easier. Over in the emulator, you can see those values on the 5th and 6th row, and we're using the align directive again to pad them out to 16-byte boundaries here in the assembled output. Back at the top, things kick off just like before, setting up our X and Y registers and setting D with our loop end. Now, here comes our first trick. I said we'll do a 2's complement to the subtrahend, the number we'll be subtracting, but actually it works out a little better if we split that into an increment here to the minuend, the number we'll be subtracting from. And then we'll be able to invert the bits on a byte by byte basis later. One important consideration is that incrementing the least significant byte of the minuend could cause a carry if it's an FF, and in that case we'd need to ripple that through the value just like we do for a carry in the long addition. Here I'll ignore it for brevity, but if this was a general purpose long subtraction routine, we'd need to handle it. With the increment done, we can go into the byte by byte loop just as with addition, and all that we do differently is a logic not here to the next subtrahend byte before adding. That's it. That's the only differences, and the carry handling is exactly as before. OK, let's give the code a run in the emulator. And there we go. 2,520 cycles later, we have our results starting in the 5th row at address 40 hex. Scrolling to our expected result, we can see we've got what we're after. But note there's this errant 1 stuck out here at address 4A. Where does that come from? Well, that's a carryover, quite literally, from adding a 2's complement value, and we can safely ignore it. But we do need to make sure there's always an extra byte available to collect these carry bits when doing long subtraction. Right, let's give this a whirl for real, and you know the routine by now. So here's the relay computer already loaded up with a program, and this time I'll bump the clock to 8 Hz, like so, and that means we'll be running at 16 cycles per second. Right, off we go. Ding indeed. And let's copy M over to the program counter, so we're pointing at the start of the result. And our first byte is 58 hex. and then with the same Arduino trick as before, we can trot through the memory for the rest of our expected result. And that is 92, 38, 3F, 35, C4, 6D, EF, AC, and finally 00. Lovely. So that's long subtraction ticked off too, and I think that'll do for this episode. Next time, yeah, there's no getting out of it, it's time to tackle long division. And although it's not one I'm particularly looking forward to, I can't calculate pi without it. That said though, we've made excellent progress so far, and I'm much farther than I thought I might get, so let's keep going. And with that, as always, thank you so much for watching, and also for all your very kind and encouraging comments, and I'll see you next time.